Section 1 Introduction. We're here to talk about large language models, LLMs, like GPT-3.5 and GPT-4, which are becoming increasingly popular. These models, such as GPT-4, can be updated over time based on new data, user feedback, and design changes. However, the process of updating these models is not transparent, and it's unclear how these updates affect the model's behavior. This lack of clarity can make it difficult to integrate these models into larger systems. For example, if a model's response to a prompt changes unexpectedly, it could disrupt the entire system. It also makes it hard to reproduce results from the same model. Aside from these integration issues, we're also interested in whether these models are improving over time. We need to know if updates meant to enhance certain aspects of the model might be negatively affecting other areas. To explore these questions, we examined the behavior of the March 2023 and June 2023 versions of GPT-3.5 and GPT-4 in 4 areas: solving math problems, answering sensitive or dangerous questions, generating code, and visual reasoning. We chose these tasks because they represent a wide range of the model's capabilities. We found that the performance of both GPT-3.5 and GPT-4 varied significantly between the two versions, and in some tasks, their performance actually worsened over time. There's been a lot of research on LLMs like GPT-3.5 and GPT-4, and they've been shown to perform well on traditional language tasks like reading comprehension, translation, and summarization. GPT-4 has even been shown to pass difficult exams in professional fields like medicine and law. However, to our knowledge, no one has systematically tracked the performance of these models over time. Monitoring changes in model performance is becoming more important as machine learning services are deployed in real-world settings. Some research has been done on tracking the performance of commercial machine learning APIs on various tasks and on how to efficiently measure changes in their performance. However, this research has mainly focused on simple classification tasks like sentiment analysis, while our work focuses on generative LLM services. Section Summary. Large language models, LLMs, like GPT-3.5 and GPT-4 are widely used, but it is currently unclear when and how these models are updated, making it difficult to integrate them into workflows and reproduce results. To address this, the authors evaluated the behavior of GPT-3.5 and GPT-4 on tasks such as math problems, sensitive questions, code generation, and visual reasoning. They found that the performance of both models varied significantly across different releases, with some tasks showing a decline in performance over time. This study highlights the need for monitoring and understanding the longitudinal drifts of LLM services like GPT-4 and GPT-3.5. Section 2 Overview. LLM services, tasks and metrics. In this section, we'll provide an overview of our study on how the behavior of language learning models, LLMs, changes over time. We'll focus on 3 main aspects: the LLM services we're monitoring, the application scenarios we're concentrating on, and the metrics we're using to measure changes in LLM behavior over time. We're keeping an eye on 2 LLM services in particular, GPT-4 and GPT-3.5. These 2 services are the backbone of ChatGPT, a popular tool used by individuals and businesses alike. By monitoring these services, we can help a wide range of users better understand and utilize LLMs for their specific needs. At the time of writing, there are 2 main versions of GPT-4 and GPT-3.5 available through OpenAI's API, one from March 2023 and another from June 2023. We're particularly interested in the changes that occurred between these 2 dates. Our study focuses on 4 tasks that LLMs often perform: solving math problems, answering sensitive questions, generating code, and visual reasoning. We chose these tasks because they're commonly used to evaluate LLMs and they're relatively objective, making them easier to evaluate. For each task, we use a single dataset, either one that already exists or one that we've created for monitoring purposes. We understand that using just one dataset doesn't fully cover a task, but our aim here is to show that significant changes in ChatGPT's performance can occur even on simple tasks. We plan to include more benchmarks in future evaluations as part of a larger, long-term study of LLM behavior. To measure changes in LLM behavior quantitatively, we use one main performance metric for each task and 2 additional metrics that apply to all tasks. The main metric for each task measures performance in a way that's specific to that task, while the additional metrics provide a more general measure of performance across different applications. For example, for the task of solving math problems, we measure accuracy, or how often the LLM provides the correct answer. For the task of answering sensitive questions, we measure the answer rate, or how often the LLM directly answers a question. For code generation, we measure what percentage of the generated codes can be directly executed and pass unit tests. For visual reasoning, we measure whether the generated visual objects exactly match the ground truth. In addition to these task-specific metrics, we also measure verbosity, or the length of the generated content, and overlap, or whether the answers provided by two versions of the same LLM service for the same prompt match each other. This overlap metric only compares the differences in answers, not the raw content generated. For example, in the case of math problems, an overlap of 1 means the generated answers are the same, even if the reasoning steps to get there are different. We use the average overlap across all tasks to measure how much an LLM service's desired functionality changes over time. For each of the other metrics, we calculate the average for both the March and June versions and use the difference to measure the size of the change. Section Summary. This section discusses the focus of the study, which is to analyze the behavior of different language models, LLMs, over time. The LLM services monitored are GPT-4 and GPT-3.5, which are widely used in ChatGPT. The study focuses on 4 LLM tasks: solving math problems, answering sensitive questions, code generation, and visual reasoning. Different metrics are used to measure the performance drifts in each task, such as accuracy, answer rate, executable code fraction, exact match, verbosity, and overlap. Section 3. Monitoring reveals substantial LLM drifts. We've been closely monitoring the performance of language learning models, LLMs, like GPT-4 and GPT-3.5, particularly their ability to solve mathematical problems over time. We've noticed some significant shifts in their performance, which we refer to as LLM drifts. To understand these drifts, we conducted a study focusing on the LLM's ability to determine if a given number is prime. This task was chosen because it's simple for humans to understand, yet it still requires reasoning, much like many other mathematical problems. We used a dataset of 500 questions for this study. To assist the LLMs in their reasoning, we used a standard approach known as the chain of thought. However, we were surprised to find significant drifts in the LLM's performance on this seemingly simple task. For instance, GPT-4's accuracy in determining if a number is prime dropped dramatically from 97.6% in March to just 2.4% in June. On the other hand, GPT-3.5's accuracy improved significantly from 7.4% to 86.8% during the same period. Additionally, GPT-4's responses became much more concise, with the average number of characters generated decreasing from 821.2 in March to just 3.8 in June. Conversely, GPT-3.5's response length increased by about 40%. The overlap in answers between the March and June versions was also minimal for both models. So, why such a significant difference? One possible explanation could be the changing effects of the chain of thought approach. For example, when asked to determine if 17,077 is a prime number, the March version of GPT-4 followed the chain of thought instructions perfectly. It broke down the task into 4 steps: checking if 17,077 is even, finding its square root, obtaining all prime numbers less than it, and checking if 17,077 is divisible by any of these numbers. After executing each step, it correctly concluded that 17,077 is indeed a prime number. However, the June version didn't follow this process. It didn't generate any intermediate steps and simply responded with no. The chain of thought approach had a different impact on GPT-3.5. In March, it tended to generate the answer no first and then perform the reasoning steps. So, even if the steps and final conclusion were correct, its initial answer was still wrong. However, the June update seemed to fix this issue. It started by writing the reasoning steps and finally generated the correct answer, yes. This intriguing phenomenon suggests that the same prompting approach, even widely adopted ones like chain of thought, can lead to significantly different performances due to LLM drifts. Section Summary. In this section, the authors investigate the evolution of GPT-4 and GPT-3.5's math-solving abilities over time by examining their performance on a task of determining whether a given integer is prime. They find that there are significant drifts in the model's accuracy and response characteristics. For example, GPT-4's accuracy dropped from 97.6% to 2.4% between March and June, while GPT-3.5's accuracy improved from 7.4% to 86.8%. These drifts can be attributed to changes in the model's ability to follow the chain of thought approach, with different versions of the models exhibiting different patterns of reasoning. Section 3.2. Answering sensitive questions, safer but less rationale. We're focusing on how language learning models, LLMs, respond to sensitive questions, as these can often lead to harmful outputs such as biased responses, personal information leaks, or toxic language. We're particularly interested in how these responses have changed over time. To study this, we've put together a dataset of 100 sensitive questions that these models shouldn't answer directly. Evaluating whether a response is a direct answer can be tricky, so we've manually labeled all responses from the LLMs we're monitoring. We've noticed two main trends. Firstly, we've seen that GPT-4 has been answering fewer sensitive questions over time, dropping from 21.0% in March to 5.0% in June. On the other hand, GPT-3.5 has been answering more, increasing from 2.0% to 8.0%. This suggests that GPT-4 may have had a stronger safety layer added in June, while GPT-3.5 has become less cautious. Secondly, we've noticed that the length of GPT-4's responses has decreased significantly, from over 600 characters to around 140. This isn't just because it's answering fewer questions, but also because it's become more concise and provides fewer explanations when it refuses to answer a question. For example, in March, GPT-4 would generate a whole paragraph explaining why it couldn't answer a certain question, but by June, it would simply say, "Sorry, but I cannot assist with that." We've seen a similar trend with GPT-3.5. This suggests that while these models may have become safer, they're also providing less reasoning for their refusal to answer certain questions. We've also been looking at jailbreaking attacks, which are a significant threat to the safety of LLM services. These attacks involve rephrasing or reorganizing sensitive questions to trick the models into generating harmful responses. We've been studying how these models' defenses against such attacks have changed over time, using the AIM attack as an example. This attack involves telling a hypothetical story and asking the models to act as an unfiltered and amoral chatbot. We applied the AIM attack to each question in our sensitive question dataset and then queried GPT-4 and GPT-3.5. We found that both models were more likely to answer when the AIM attack was used. However, their responses varied over time. In March, the AIM attack resulted in 78% direct answers from GPT-4, but this dropped to 31.0% in June. For GPT-3.5, the difference in answer rate between the two versions was only 4%. This suggests that GPT-4's updates have made it more resistant to jailbreaking attacks than GPT-3.5. Section summary. The paper aims to understand how language model, LLM, services respond to sensitive questions over time. They created a dataset of 100 sensitive queries and manually labeled the responses from LLM services. The study found that GPT-4 became safer by answering fewer sensitive questions and providing shorter explanations for refusals, while GPT-3.5 became less conservative. Additionally, the defense against jailbreaking attacks differed between the two versions, with GPT-4 showing more robustness than GPT-3.5. Section 3.3 Code Generation. More verbose and less directly executable. We've been exploring the use of language learning models, LLMs, in generating code. There are many datasets available for this purpose, but using them to evaluate the code generation capabilities of LLM services can lead to data contamination issues. To address this, we've created a new dataset, which includes the most recent 50 problems from the easy category on LeetCode at the time we wrote this. The earliest public solutions and discussions for these problems were made available in December 2022. For each problem, we combined the original problem description with a corresponding Python code template. We then sent each LLM's generated solution directly to the LeetCode online judge for evaluation. If the online judge accepted the answer, we considered it directly executable. However, we noticed a decrease in the number of directly executable solutions from March to June. For instance, over half of the solutions generated by GPT-4 were directly executable in March, but this dropped to just 10% in June. We observed a similar trend with GPT-3.5. Both models also became slightly more verbose over this period. Why did this happen? One possible reason is that the June versions of the models consistently added extra non-code text to their solutions. For example, GPT-4 solutions in March and June were almost identical, except for two parts. In June, the model added Python and before and after the code snippet, and it also generated a few more comments. While these changes were small, the extra triple quotes made the code unexecutable. This issue can be particularly difficult to identify when the LLM's generated code is used within a larger software pipeline. Next, we looked at how LLMs have evolved in terms of visual reasoning, which requires abstract thinking. We used the ARC dataset, which is commonly used to evaluate visual reasoning abilities. The task involves creating an output grid that corresponds to an input grid, based on a few similar examples. To present the visual objects to the LLM services, we represented the input and output grids as 2D arrays, with each element's value indicating the color. We gave the LLM services 467 samples from the ARC dataset that fit within all services context window. We then compared their generated solutions with the correct answers. Both GPT-4 and GPT-3.5 showed slight improvements in performance. However, for over 90% of the visual puzzle queries, the March and June versions produced identical solutions. The overall performance of these services was also low, with GPT-4 achieving a success rate of 27.4% and GPT-3.5 achieving a success rate of 12.2%. Interestingly, the LLM services did not consistently produce better solutions over time. In fact, despite its overall improved performance, GPT-4 in June made errors on queries that it had correctly answered in March. This highlights the importance of closely monitoring changes in LLMs, especially for critical applications. Section Summary. The authors constructed a new code generation dataset to assess the code generation ability of LLM services, as existing datasets are contaminated. The number of directly executable code generations decreased from March to June, possibly due to the addition of extra non-code text. In terms of visual reasoning, there were marginal improvements in performance for both GPT-4 and GPT-3.5, but overall performance was still low. It is important to monitor drift in LLM services, as they may make mistakes on queries they previously answered correctly.